This is how we deal with the imbalance class problem. So as we can see in this figure, the distribution of background is more dominant than vessel pixel itself. So to solve the imbalance problem, we use a patch approach as input of units. So this patch is generated only from a field of view area. So it's mean only in this circle area. So the size is 48 times 48 pixel. And then after patch generated, so patch are selected only if they have more than 50 pixel or 50% pixel for the vessel. So otherwise patches with less than 50% vessel will be removed. So after selecting the parts, so we use this as input of the unit. So by use this approach, the imbalance problem can be minimized because the distribution of vessel and background is almost same. This is the result of vessel segmentation between baseline and graph-based smoothing regularizer. So the first column is a result of the baseline, and the second column is the result from baseline with our graph-based smoothing regularizer. So from this figure, we can see the baseline of unit is good for segmenting, but failed small vessel. But with graph-based smoothing regularizer, the segmentation result is better and smoother than baseline unit without a regularizer, especially in the small part of the vessel. In this figure, we also saw the ROC curve on this image. So the ROC curve is created by plotting the true positive rates against the false positive rate at various threshold setting. So it means ROC curve summarize the trade-off between true positive rate and false positive rate. So true positive rates suggest a better ability of segmenting vessel, and false positive rate is indicate a better ability classify the background pixel. In this figure, we also saw precision recall curve of this image. So precision recall curve is created by plotting the precision against the recall at various threshold setting. Its main precision recall curve is summarize the trade-off between precision and recall. The blue line is for baseline without regularizer, and the orange line is for our graph-based smoothing regularizer. So we can see in the both of the curve is we get a better curve than baseline without regularizer. This is the performance comparison of the unit baseline with graph-based smoothing. So we measure the performance with the sensitivity, specificity, accuracy, and ROC. And then also we adding some experiment according to Rajeev Sensei's suggestion with the Jacquard and F1 score and precision recall curve. Here we just use the area under curve of precision recall curve and area under curve of ROC curve. Here, in general, this table show there are improvement of all measurements between baseline with the regularizer. For example, a combination of binary cross entropy with Graph smoothing regularizer is better in almost in all measurement, if compared with the only using binary cross entropy. And combination dash loss with graph-based smoothing regularizer also we get the better result than using only dash loss. So this is the comparison with the state-of-the-art method. So we compare our proposed method with existing method in this field. So we can see in this table, our method is getting the comparable result with the existing method. Now we're going into chapter 3. So this section, I will explain more detail about our second proposed method, graph Laplacian regularizer based on pixel difference. So different with the previous chapter, in this work, we construct the graph Laplacian deriving by two images from prediction and ground truth. So in other hand, the adjacent symmetric is defined by the differences of neighboring pixel to instead of the similarity between pixel. So in this figure, the first column is so that we calculate the GLRDN after the convolution neural network. And then the main idea of this regularizer is to use the differences of pixel with their neighborhood as additional information in learning process of CNN. So let's assume we have a predicted image from CNN and then target image. So in this figure, the second column is from prediction image and target image. We construct the graph G, which is consists of vertex V and edges E. Here, V is set of index pixel, which is represented as node or vertex, and A is neighboring relationship pixel represent as edges. Then from this graph, we define the differences of neighboring pixel SG. SG is calculate the differences between the differences one pixel with their neighbor pixel in the target image, and the differences of one pixel with their neighboring pixel in the prediction image. Then we can get the different metrics delta t and delta y. So delta t means the different metric from target image, and delta y is the different metric from prediction image. And then the next step, we can derive to get the incident matrix B, and then generate graph Laplacian metric of L. Then we combine the differences term SG with the standard loss function. Here, ABCE means binary cross entropy loss function. And this is the parameter lambda. This parameter is used to control the effect of regularizer. This is the comparison result of our GLRDN. So the first column is full image, and the second column is selecting selected region from this image, and this is the ground truth, and this is a result without a regularizer, and this column is showing our result with the GLRDN. So we can see without our proposed regularizer, the result is missed lot of small or thin vessel. But with our proposed regularizer, the small vessel can appear correct, detecting very well. And this is the performance comparison for between baseline with the GLRDN regularizer. So in this table, in general, the table show improvement in all measurement between baseline with the regularizer. And combination like this one, combination binary cross entropy with GLRDN is get improvement than only using binary cross entropy. This also in the combination of dash loss with GLRDN is have a better result than only using dash loss. This is the performance comparison of GLRDN with the state-of-the-art method. So here we only using specificity and sensitivity, accuracy and ROC, because almost research work in this field only reported the work only using this measurement. So we don't have data to compare with another measurement like Jacquard F1 score and precision recall curve. So here, our proposed method get improvement or comparable with the other existing method. Now we going into chapter 4. So in this chapter, I will explain more detail about the last our proposed method. So the regularizer based on Euler characteristic. So Euler characteristic is a global topology which is invariant to all topological transformation like rotation and scale. So generally, Euler characteristic of two-dimensional image is considered to be the number of connected components. And the objective function of a Euler characteristic is calculated based on the relationship between the number of vertices P, side S, and F, face F, like this form. So the Euler characteristic can be used to know the number of isolated objects or connected component in the image. For example, in this figure, we have a simple two-dimensional image. So to know the Euler characteristic of this object, the first we calculate the number of vertices P and the number of sides and the number of face like this showing in this figure. In this example, we get the 19 vertices, 33 of sides, and 16 of face. And finally, we found that Euler characteristic of this image is 2. This is related with the number of connected components of this image. To address the invariant problem, we consider the constructing vertices, side, and face into different directions. This is the first direction, and the second direction is the opposite direction. Then Euler characteristic is calculated for its direction. AC1 is for first direction, and IC2 is for second direction. And by calculate the average of two Euler characteristic with a different direction, invariant problem can be solved. In this slide, I demonstrate how to include the Euler characteristic as a regularizer in the convolutional neural network. So let's assume we have a predicted image from the convolutional neural network. And from the output of the CNN, we analyze the prediction image and calculate the number of isolated objects by finding their Euler characteristic. And then to address the invariant problem, so we consider to calculate the Euler characteristic by two directions and then calculate the average of two directions. And then finally, the total number of isolated object A is considered by computing the average between two directions and combine this information with the binary cross entropy loss function or dice loss. To make it simplify, so this is the general framework we use in this experiment. Same with the previous method, we use U-Net in this experiment. So after we get the output from the U-Net, we analyze the output and then calculate the number of vertices, side, and face, and then calculate the Euler characteristic and get the isolated object. Then use it as regularizer and combine with the standard loss function of CNN. This is the ablation study of the Euler characteristic regularizer. We experiment with 3 datasets. The first is drive dataset, and then start dataset, and just DB1 dataset. For each dataset, we show the result baseline. We compare with the baseline with the Euler characteristic. So we can see in this table, we can get the improvement for each dataset. So in almost of all measurement. And we also we can see this figure also. We get a better ROC and precision recall curve for each dataset. And this is the visualization result for Euler characteristic regularizer. So we can see in this, the first image is the fully image, and the second image the selected region from the fully image, and this is for ground truth image, and this is without a regularizer, and this is for proposed regularizer. So here, the proposed network with regularizer perform well in segmenting disjoint facial connection better than architecture without a regularizer. This is the ROC curve and precision recall curve comparison between baseline with the proposed regularizer on a drive dataset. So as we can see, the curve is so the Euler characteristic regularizer has a better ROC curve than baseline curve. And also in precision recall curve also show that our regularizer has a better curve than baseline curve. And this is ROC comparison and precision recall comparison in star dataset. So in star dataset, we can see in this figure, we also get a better curve than baseline without regularizer. And this is the curve for ChessDB1 dataset. So in ChessDB1 dataset, we also get the better curve than a baseline without regularizer. And as additional experiment, we also use Euler characteristic regularizer in a different way, like this. So in this slide, we use Euler characteristic regularizer based on the differences of number of isolated objects between prediction image and then ground truth image. Here, A1 is the number of isolated objects for prediction image, and AT is the number of isolated objects for a ground truth image. So different with the previous regularizer, it will force the number of isolated objects between the output and the ground truth to be equal or more closer. So this regularizer will lead the large error if the number of isolated objects between the output and ground truth is not equal. Otherwise, it will produce zero or small error in the detecting the facial region. For this experiment, this is the additional experiment. So in the preliminary defense, we didn't show this experiment. So we get this after the preliminary defense. So this is the performance comparisons of the Euler characteristic between prediction and ground truth. We try in its data set. Here, baseline means is only unit without our regularizer, and AC odds means we use Euler characteristic regularizer only in prediction image, and AC odd GT means we use Euler characteristic on the prediction image and ground truth image. So in this table, we can see by define the differences of number of isolated objects between prediction and ground truth, we got some improvement in some term measurement. For example, here for ROC and precision recall curve. The good improvement in the STAR dataset and ChessDB1 dataset, which is the reason why the improvement is good is because the condition of its dataset is different, and STAR dataset and ChessDB1 dataset is more noisy than Drive dataset, and also many pathologies region are found on the STAR dataset and ChessDB1 dataset. So in such condition, using the differences of Euler characteristic between prediction and ground truth image bring the better improvement. This is the comparison method of a Euler characteristic with the state-of-the-art method. So here with our proposed method using Euler characteristic in the prediction output, we got good improvement. For example, here ROC achieved 98%, and using Euler characteristic in prediction and ground truth image, we got achieve ROC of around 98%. In this slide, we investigate the measure of complexity of learning of our approach over the other methods during the inference stage. So we choose the computational complexity of deep learning and deep learning methods. Complexity of learning between deep learning and non-deep learning method has found that our approach is not showing much difference compared over the other methods. And there is no different time between baseline with our proposed methods. So the measure of complexity of learning time of baseline unit is almost similar with the proposed method. It indicates the addition of the regularization term with the existing architecture not tend to increase the execution time. And here, the complexity of learning, our approach is not sensitive to the performance detection. Finally, this is the performance comparison between graph-based smoothing, GLRDN, and Euler characteristic regularizer in one table. So according this table, so all proposed regularizer bring the good performance in all metrics measurements if we compare then baseline. So from three proposed regularizer, GLRDN has higher result of in the term of ROC and precision recall curve than other regularizer. And graph-based smoothing and Euler characteristic has comparable result of ROC and precision recall curve. So now we're going to chapter 5. This is a conclusion of our study. So this study takes advantage of the neighboring pixel information in the image. So as additional information on the convolution neural network. So this information is constructed as a regularization term in the objective function. So all proposed method is use neighboring pixel relationship as a regularizer to promote the accuracy of the estimate segmentation result. And all proposed methods are applicable for other application like super resolution, object detection, and other application. And then our proposed method is effectively reduce the segmentation error and reconnected the small fragmented vessel. And compare with the baseline architecture regularizer, the proposed approach demonstrates improvement in enhancing the tiny vessel on various types of data sets. This is our publication, which is correlate with the study. So the first is regularizer based on Euler characteristic for retinal blood vessel segmentation. And the second is improvement for single image super resolution and image segmentation by graph Laplacian regularizer based on differences of neighboring pixel. And then the third is the conference paper UNet with graph-based smoothing regularizer for small vessel segmenting on Vandas image. And this is the related publication during our study. We have two related publication in single image super resolution reconstruction based on the differences of neighboring pixel and transfer learning by cascade network to identify and classify a lung nodule for cancer detection. So that's all my presentation, and thank you for joining and listening our presentation.
Okay.
Thank you.
Okay. Thank you for the presentation. I'd like to start my very general question.
Yes.
The first question is yes or no question. Did you enjoy your PhD research?
Yes, Sensei. I very enjoy our life in our study and research environment in this study, in this laboratory.
Okay, next one is, what is the most excited during your PhD research?
Okay, the most exciting moment in during my PhD student is if we got the good result from our idea. So you know, so after we got the improvement in our result and baseline, so this is the very exciting moment during our research in this laboratory.
And the third one, last one, is what did you learn during your PhD research?
Yeah, so during my PhD research, of course, I learning many things about research, especially from Kurita Sensei. I learning how to do the good research, how to enjoy the result, and how to make the idea, and how to make writing the paper. And the most important thing is I learned about from the Kurita Sensei, especially how to doing the research with happiness. So, and how to enjoy the result.
Okay. The next, I'd like to ask the reviewers for comment or questions. Mukaida Sensei, please.
Yeah. Thank you for your good presentation. So I have one concern. So as you know, it is well known that between the accuracy and the reduction of the computational cost has a trade-off. So in order to such purpose, you propose several techniques such as the graph Laplacian and Euler technique, etc. So
Yes.
yeah, I guess they will help for reducing a computational cost. So, although you shown the several good performance, however, there is no comment on the computational cost, at least. So,
Okay.
please comment of my concern, please.
Okay, Sensei. So thank you for your concern, Mukaida Sensei. So yes, here we investigate the complexity of our proposed method compared with the other methods. So we also investigate our proposed method with the non-deep learning method. So in the inference stage, we found that during the inference stage, we found that our proposed method actually not different with a baseline without for example, we here compare with the unit. So our proposed method compare with the unit, which is our unit is combined with our regularizer. This is no difference in the inference time. So it means our proposed method is not intend the bounded in the complexity learning time. But of course, we also compare with non-deep learning method. So a non-deep learning method is more here in this table. It's more fast, but it is comparable, I think, because we also get we have a good performance with the deep learning method. But so there are different time with no deep learning method, but I think this trade-off is still acceptable, Sensei. So this is my comment, Sensei.
Yeah. Do you have any result for the CPU time or others? If you have.
Okay. So.
Not complexity.
Yeah. So you mean so
my interest is only
Okay. So why we using the time? So not the CPU.
Yeah.
So in here we use time to measure the complexity time with the other methods. So we using only these measurements, time execution, because almost research work in this field reported by using these measurements. So to able to make comparison with the existing method, we also use these measurements to measure the complexity of our proposed methods.
Yeah. It is sufficient. Thank you very much.
Okay, thank you, Sensei.
Thank you very much.
Thank you.
以上です。
Next, Professor Eguchi, please. Eguchi sensei, お願いできますか?
Hi. Thank you for your talk. I have one question. No, two questions. Can you show me the hyperparameter setting?
Hyperparameter setting?
Like a lambda or some other hyperparameters?
Okay. Maybe in the beginning slide. Please wait, Sensei.
Yes, no problem.
This one, Sensei?
Yes. So
okay.
The hyperparameter, especially lambda, looks very small.
Yeah.
How did you select the hyperparameters like this?
Okay. So to select this parameter, we doing the experiment for only this. So we use the range of lambda from starting from the 10, and then decrease after 10 we use 1, and then use 0.1, and then 0.1 after e power 5. So from this experiment, we found that we should use we can get the better result in the this value of the lambda, Sensei.
But even if the hyperparameter lambda is so small, but it works well.
Yes, Sensei. Okay. It's very work well if the lambda is very small.
Thank you for the clarification. And one more question is, can you show me the results?
Okay.
Any results?
Any
like
result? Okay.
specificity and sensitivity
Sensei.
and some others.
Table, Sensei. You mean table? Yes. Okay.
Can you
This
say?
one?
Yes. So your method and some other methods achieves good specificity, but not so good sensitivity. But in the application of the vessel detection, the detection of the vessels, blood vessels, which is more important for such application?
So in our specificity is the ability to detect the background region, and the sensitivity is ability, the proposed method to detect the facial region. So in facial segmentation, so the most important things is to detecting the facial region. It means here sensitivity is more important, I think, than specificity, Sensei.
Okay, great. So from that perspective, your method gives a good result.
Yes, Sensei. So this is based on the experiment. We found that our proposed method contribute a good sensitivity than the baseline.
Okay, thank you. That's all my questions.
Thank you.
Thank you very much. Next is Righteous, Professor Righteous, please.
Hello. Thank you for your presentation. And I appreciate that you have incorporated my comments and requests in the final version, especially to show precision recall graphs and also Jaccard index. So I was worried that false positives can be a problem for your method, but we see from the results that you get good improvement, and also incorporating the dice loss also. Although it seems that sometimes it leads to improvement, and depending on the regularization, not so much. But so maybe one further comment in this regard is like. What is usually done is you just combine both losses, like you use both cross entropy and dice at the same time. So you can use both of them. You can take you can combine the best parts of both of these, and also like I mentioned last time, like to counteract the unbalanced data problem. This time, you mentioned that you have selected only samples which have more than 50% of foreground. Is this correct?
Yes, Sensei. 50% for facial pixel or foreground pixel.
It seems a little bit strange. Like from these images which you showed, do they actually have 50% vessels on them?
This is just here. I make this visualization just for example, Sensei.
Okay. Because that doesn't seem to have 50%.
Yeah. So of course we see in this. This is just for visualization. Sorry. So it's but actually in the application we selecting the pixel if more than 15% pixel. So
okay. So I was thinking this is just a comment that instead of just not using any patches which have less than 50% vessels, it might be more useful to use some kind of like focal loss, which you just add a term in your binary entropy loss so that you just punish you just use only difficult samples. So in this way, you don't need to have to throw away some data, because some patches which don't have 50% like vessels might contain very useful information. So I was thinking, yeah, you maybe you, but anyway, you're using a lot of data, so maybe not so problematic. But I think another solution would be just to use something like a focal loss. And anyway, I think dice loss also is good to counteract unbalanced problem. I think this is okay. So I just wanted to just to make sure, like last time I also asked you about this, but I just want to confirm that I understand this correctly. Can you show the slide on which you define this similarity for the first two methods?
For the first method.
Yeah, you defined similarity, in which you define this the graph Laplacian regularization. Yeah, this one, okay. Yeah, maybe. Okay, yeah. So this is also okay. So if I understand correctly, you're trying you're trying to use to compare the differences between ground truth and the differences between the outputs. So you want to make them similar. You want to make them so when the ground truth, the difference between neighbors in ground truth is small, you want the difference between the output to be small, and so on. So here, do you define this over the whole patch, or is it only over the neighbors, like 8 neighborhoods? I think I was asked last time, but I'm not sure if
yeah. So this is technically it's same. We define this calculation only from the 8 neighboring pixel to the first is to reduce the computational cost, but in other hand, we use sum up all in this equation. So implicitly, from this local neighborhood correlation, we sum up for all the pixel in the image. So implicitly, we all pixel in the image will contribute to the regularization value.
Yeah, they'll contribute, but what I want to know is, like, for instance, if you have one pixel in the left upper corner,
left
and
upper
if you
corner.
have another pixel which is let's say in the bottom right corner,
yes.
So if the value, the difference between these two pixels, do you incorporate it in this cost, or you're only looking at the neighbors?
Yeah, we including this. So we including these differences of the between one pixel in the prediction image with all neighboring pixel in the 8 neighboring pixel, and then the differences between one pixel with the 8 neighborhood pixel in the target image, and we try to make the differences is between one pixel with the 8 neighborhood to be small or
Lakuman-san, not 8.
Yes.
4 neighbor.
4. Sorry, yes. In the image is 4 neighbor.
Okay, so the reason I'm asking this is because I just wanted to make sure that, are you using global information, or you're using only local information? Because if you just consider pixels in the neighborhood, this would be kind of local information. And if you have pixel, like you can have a very long edge, very long vessel. So if you have this pixel here is on and this should be on, do you consider this very large distance pixels which are at very large distance? Do you consider their values also, or you only take this in the neighborhood?
So the first we calculate this only the local neighborhood, but in the finally we sum up all of the local neighborhood to get the global connectivity. So I think the implicitly by sum up of the local information from the local and from each local, so we can get the global correlation.
Okay, so yeah, because recently, there is this like state-of-the-art methods which use transformers. They usually incorporate both local and global information. So I was wondering whether you're trying to do something similar, or it's more kind of like a local method. Okay, so yeah, maybe you should try to compare this with some of these methods to see whether how your method compares with this. Mm-hmm. And another thing which I wanted, I actually have a lot of questions, but it seems we already over time. So is it okay? Maybe leave
okay,
time for guests to ask some questions.
Okay, I'd like to ask to other.
Okay. So
and then we can return.
Okay.
Miyao Sensei, please.
Okay. Thank you for your presentation.